Hi everyone, today we're looking at Unit 5, Lesson 7, Optimization Problems. So when we think of optimization, we should be thinking of our optimal value. So we're going to talk about how that ties back to some of the key points we've learned in terms of our quadratic. So the maximum or minimum value of a quadratic always occurs at the vertex. So let's just highlight and remember that. The maximum or minimum always occurs at the vertex. The maximum or minimum could also be called our optimum value. So remember, when our parabola opens up, we have a minimum, but that's still our optimum. And when our parabola opens down, we're going to have a maximum for our vertex, considered our optimum. When we're trying to solve these optimization problems, we have to think about how we're going to approach them. So one thing I'm going to include in here that's not suggested is that you should try to draw a picture if you can. I'll put if possible. Okay, we're going to assign variables using let statements, and we did that back when we were doing linear systems, basically stating what the variable is going to equal, and then determine equations using the given information. And these equations that we're coming up with should result in some type of quadratic equation. So depending on what form we get these equations in, then we'll talk about what method should we use to solve for them. So we know there's three forms of our quadratic that we've learned. We've learned standard form. We have learned factored form. And we have learned vertex form. Those are the three forms of the quadratic that we've learned about in the past couple units. So based on what the question's asking you, you are either going to be looking for your zeros, or you're going to be looking for your optimum value, which we would say is our max, our min, or our optimum value. That's all the same thing. So how do we go about doing that? Well, if we're in standard form and we need to find our zeros, we have to think about, well, which method gets me my zeros? And we know that's in factored form. So if we're in standard form and we want to find our zeros, we're going to have to factor to do so. If we're in standard form and we want to find our maximum or our minimum, that means we're looking for our vertex. So that means we have to go from standard form to vertex form. And the process for doing that, which we've learned in the previous few lessons, is we would need to complete the square. If we have an equation in factored form and we're trying to find those, say, key points, so let's say we're trying to find our zeros, or we're trying to find our optimum, which we would call our max, our min, or optimum. How would we go about finding these key points from factored form? Well, from factored form, we know we can pull the zeros right out of factored form. So we'll just say read from form given. Right? In factored form, we know we can easily take those brackets and identify what our zeros are. If we're in factored form and we need to find our vertex, we know we first have to find the x value of our vertex and then the y value of our vertex. So to do that, we find the midpoint of x, and then we sub that in to find y. Okay, the last form that we have been talking about is our vertex. So same idea. If we're in vertex form and we want to find our zeros, or we want to find our optimum value, which will be our minimum or our maximum, how would we go about doing that? So when we're in vertex form and we want to find our zeros, remember our zeros are the same as our x-intercepts. So we would set y equal to 0 and solve for x. If we were trying to find our maximum or minimum, that is just our vertex. So if we're in vertex form, we should be able to easily just read that right from the form given. So we'll say read from form, right? It's given to us because it's already in vertex form. So after you've determined whatever you're trying to find, whether that be your zeros or your optimum value, you should always finish things off with a therefore statement. And I guess that should be number 5 because I didn't leave this one. So if we're trying to then solve using one of those strategies we discussed, that would be like step 4. And then we'd finish things off with a therefore statement. So let's look at a few optimization problems. And when we hear optimization, right, we should be thinking max or min. So generally what we're going to be looking for today is the vertex for whatever these word problems are asking us to find. So the first question says, a rectangular lot is bordered on one side by a stream and on the other 3 sides by 80 meters of fencing. Use the dimensions of the lot, find the dimensions of the lot if its area is to be a maximum. Okay, so we know a couple of things here. We know area. We have a mathematical equation for that maybe we can use in this problem. Area equals length times width. And when we see the word maximum, we should be thinking, okay, I need to find the vertex because maximum and minimum represent our vertex. But before we get into that, let's start by drawing a picture. So we have a rectangular lot. One side is a stream, but there are 3 other sides to this lot. Okay, so we know that we're going to have the width of this lot and the length of this lot. We don't know what those values are yet. But it does say that the distance around them, right? Because it says the 3 sides will be fenced with 80 meters of fencing. So we do know that the width plus the length plus the width is going to equal 80 because that 80 meters of fencing. So if we wanted to rearrange this, right, we could say, okay, well, if I have L here, can I rearrange for L? Well, I could say L equals 80 minus W, or L equals 80 minus 2W. So we'll put that with our length. Let's go ahead and write a let statement for all these variables we're using. So let's let W represent the width of the lot. Okay, and we will let L represent the length of the lot. So remembering that we have area equals length times width, maybe we can plug in some information now. We know that we're trying to maximize the area. So whatever we do, however we set up this equation, we need to eventually get it into vertex form so we can identify what the maximum would be. So if we know area equals length times width, well, we can look back at our picture and identify we have our length here and we have our width here. So we can plug those in for our length and our width. So we're going to have area equals length, which is 80 minus 2W times W. So we'll expand and simplify. So we'll get 80W minus 2W squared. So this is starting to look like standard form, but let's just rewrite this so it looks like our normal standard form. So let's sort into standard form. And all I mean by that is we'll put our squared term at the front. So we'll have negative 2W squared plus 80W. Okay, so I'm going to come back up here to my table now. I'm trying to solve this. I've determined my equation. It looks like a quadratic equation. We've gotten a quadratic equation in standard form. We need to find our maximum. So if we have an equation in standard form, the way that we're going to do that is we're going to complete the square. Okay, so we're in standard form. We need to find our maximum or our minimum, whichever. In this case, it's our maximum. So we're going to complete the square to do so. Okay. So let's just make a note here. Let's complete the square. So to complete the square, we're going to factor out that negative 2. We're going to be left with W squared minus 40W. And then I'm going to leave room in my bracket to add whatever I need. Remembering that I have to take my b term, I have to half it, and I have to square it. So if I do 40 divided by 2, that's going to be 20, and 20 squared is 400. So that means I'm going to add 400, and I'm going to subtract 400 to complete the square. So now I need to take that negative 400 and I need to move it outside my set of brackets. When I move it outside my set of brackets, I have to remember to multiply it by the negative 2 that's connected to everything inside that brackets. Finally, from there, I will factor that perfect squared trinomial I've created. So w squared minus 40w plus 400. So the square root of w squared is w. The square root of 400 is 20. And that sign in the middle is what goes between them. We'll have w minus 20 squared. And then minus 400 times a negative 2 is a plus 800. Okay, so this is now our equation in vertex form. So we have to think about, when we look at our equation, what is where my x usually is and what is where my y usually is. Let's identify our vertex first. So our vertex is going to be at 20 and 800. Well, if we look back up at our original equation, where x usually goes, we have a w. So we can say this is usually our x value. Where our y usually goes, we have an a, right? So that means that's usually my y. So as we're looking at our vertex, we can identify, okay, that my x value represents the width, and my y value is going to represent the area. And in this case, it's going to represent the vertex of this situation, right? Or the maximum or minimum. So if I was going to draw a rough sketch, I know that width goes along my x-axis, and I know the area goes along my y-axis just based on the problem. And we're going to have a parabola that does something like this, when it has a vertex at 20 and 800, okay? So we can see then from that our maximum area is going to be 800, but the question is asking us to find the dimensions. So we need to find the dimensions that make that maximum area of 800. So let's do that as well. So I'll just come over here. And we can say, well, we know width will equal 20. Length is going to equal 80 minus 2 times my width, or 2 times 20. So length is going to equal 40. So we can say, therefore, the lot will have a max area of 800 meters squared with dimensions of 20 by 40. Just squeezed them in there. Okay, so we found the maximum area will be 800, and that means it will have a width of 20 and a length of 40. Okay, so let's look at another word problem and take a look at how we go about doing that. So now I'm in factored form. I need to find my maximum. So we can do that by finding the midpoint of our x's and then sub that in to find our y, which will give us our vertex. So let's go back to the problem and do that process. It says a bus company carries about 20,000 riders per day for a fare of 90 cents. A survey indicates that if the fare is decreased, the number of riders will increase by 2,000 for every 5 cents of decrease. What ticket price would result in the greatest revenue? So not so much a picture we can draw here, which is why I said, if possible, draw a picture. But if we take a look, we should underline or point out some key information. So it says this bus company has a fare, right? So we should be thinking maybe we're going to have to do something with that fare, because that's a number being provided to us. We know the fare right now is 90 cents. It says a survey indicates that if the fare decreased, so if there was a decrease in fare, the number of riders will increase by 2,000 for every 5 cents of decrease. What ticket price would result in the greatest revenue? So greatest revenue, that sounds like to me maximum. So we're trying to find our maximum revenue. Okay. If we're trying to determine what the decrease should be, it's saying that when it decreases the fare, it's going to do so in 5 cent increments. So let's let X represent the number of 5 cent changes in fare. Right? Because they're not going to go down by 1 cent. Every time they go down, they're going to go down by 5 cents. So if X was 2, that means there was a 10 cent change in fare. If X was 4, there's a 20 cent change in fare, and so on. If we're trying to determine our revenue, we have to remember, how would we calculate revenue? Well, revenue is going to be equal to whatever the price is being charged times the number of riders. So we're going to see if we can plug in some information to help us with this. Okay, we'll call R our revenue. Our price is going to be represented by, we know it's going to be 90 cents, right? We have that 90 cents, but they're looking to decrease it by some amount of 5 cent changes. So we could say 90 minus 5x, okay? Because both of those represent cents. So if there was one decrease in price, it would be 5 cents times that one that we'd be decreasing from the 90 cent fare. So that's why that little algebraic expression would represent price. In terms of the number of riders, it says they generally carry 20,000. But there's going to be an increase of 2,000 for every 5 cent decrease in price. So we have created an equation here that looks like we could expand and simplify and get it into a quadratic. So let's expand and simplify to standard form. So we'll have that R equals, we multiply 90 times 200,000, no, 20,000. Then 90 times 20,000 is going to be 1.8 million. And then if we multiply our outside terms, we're going to have 90 times 2,000, which is going to be a positive 180,000. Our inside terms, 180,000x. Our inside terms, we're going to have a negative 5x times 20,000. So that'll be a negative 100,000x. And then we'll have our last terms, which is a negative 5x times 20,000 is going to be a negative 100,000 x squared, or 2,000, so that's a negative 10,000, sorry, x squared. Okay, so we're just going to reorder this so that we have it in our standard form that we're used to seeing it in. So we'll write that negative 10,000 x squared, and then we have 180,000 x minus 100,000 x, which will be just 80,000 x, and then it'll be plus that 1,800,000. Too many zeros. Okay, so now that we're here, we're trying to figure out the maximum. So if we need that maximum, we're going to find our maximum. We're in standard form. We got to get it to vertex form, so we have to complete the square. So when we're completing the square, we're going to start by common factoring out that a term, but just from my first two terms. We'll have a negative 10,000, and we'll have x squared. And if we take a negative 10,000 divided from 80,000, we're going to have a minus 8x. Okay, and then I'm going to leave some room in my bracket so that I can add or minus, add and subtract whatever that number is I need to make that a perfect square trinomial. And then we'll have 1.8 million out here. Okay, so inside my bracket there, I know I need to take my b term. I'm going to cut it in half, and I'm going to square it. So 8 divided by 2 is 4. 4 squared is 16. I'm going to add 16, and I'm going to minus 16 inside my brackets. So I'm going to have a negative 10,000. And we'll have x squared minus 8x plus 16. And we'll bring that negative 16 out, remembering to multiply it by that negative 10,000 when we do so, plus 1.8 million. Okay, so from there, we'll make sure that we know how to factor that perfect square trinomial. So x squared, square rooted is x. The square root of 16 is 4. And then there will be a minus between them because that's the sign on our middle term. And then negative 16 times a negative 10,000 is going to be a positive 160,000 plus 1,800,000. So we'll finally just combine those constants at the end. So we'll have plus 1,960,000. Okay. So that gives us a lot of information. Keep in mind that when we look back at our original equation, right, x is where our x usually is. And we said what x represents. X represents our 5-cent changes in fare. And then r is where our y usually is. So when we're talking about our vertex, we know that x represents the change in fare and y represents our revenue. So we can say our vertex is at 4 and then 1,960,000. So we could identify that. That's the number of 5-cent changes, because that's x. And the y represents our revenue. So looking at that, we can see that there's going to be 4 5-cent changes. So if we wanted to figure out, okay, well, what's the change in price going to be? We're going to have 4 price decreases of 5 cents. So our price is going to be, the original was 90, but we're going to subtract from that 5 times 4. So that's 20 cents. So the new price is going to be 70 cents. Okay. So I'm just going to come back over here for my therefore statement because we have a little bit more room. So we'll say therefore the max revenue of 1,960,000 will occur when the fare is 70 cents. Okay? So we were able to figure out what that fare would be because we assigned a variable to it, and then the revenue as well because that was the y value that we created in our equation. Okay, one more word problem for today. So it says a rectangular field will be fenced on all 4 sides. There will also be a line of fence across the field parallel to the shorter side. A lot of information. We're going to draw a picture in a minute. If 900 meters of fencing is available, so that gives us a number to work with. We have 900 meters of fencing available, and when we think fencing, we should be thinking perimeter because fencing is going to go around the outside of a shape. Then it's asking us what dimensions will produce the maximum area. So we're looking for our dimensions, and remember when we see maximum area, we should be thinking vertex. Okay, but we also know the area equals length times width. Okay, so let's draw a picture of what's going on in this situation. It says we have a rectangular field like this. Okay, so we have a rectangular field. We'll say that this is our length and this is our width. It's going to be fenced on all 4 sides. There will also be a line of fence across the field parallel to the shorter side. Okay, well, this is my shorter side. So if I drew a line of fence that was parallel, maybe somewhere over here, then that would represent another piece of fencing that needs to happen. So it says a rectangular field will be fenced on all four sides. There will be a line of fence across the field parallel to the shorter side. What dimensions of the field will produce the maximum area? So we know now, based on where all of the fencing is going, that we're going to have a length here, we're going to have a width here, and we're going to have a width of fencing there as well. So if we were trying to represent our perimeter, we can see that we have 2 lengths, plus we have 3 widths that we're going to need to cover with fencing. And we know that the perimeter of all of that is going to be 900. So let's let, just like in the other one, let's let W represent width, and let's let length represent, or L represent length. Okay, once we have our perimeter, we can always rearrange for one of the variables so that we're only working with one. Okay, so let's just rearrange for our length. So then we're just working with just length when we plug into a formula. So I could say 2L is going to equal 900 minus 3W. And then I could divide both sides by 2. So I would say 900 minus 3W divided by 2, which means my length is going to equal 450 minus 1.5 W. Okay, remember, we are trying to find our maximum area. So if we have the L equals that, and we have our W, we can plug this in. So we're going to sub into our area formula. So if area equals, my length is going to be 450 minus 1W. Need a little more room. So my length is 450 minus 1.5W. That's my length, times my width, which is W. Okay, well, we could expand and simplify this, or we could take a look at this and recognize that we're actually in factored form. Right, so this is a factored form of a quadratic. So if we're in factored form and we need to identify our maximum, which is our vertex, let's go back to that. If we're in factored form, we can find our zeros. So I can take both of my brackets and set them equal to 0, right? And then solve. So I'll have 450 equals 1.5 W, and then I'll divide both sides by 1.5. So we'll get 300 equals W. So my zeros are going to be at 300 and at 0. So I'm going to find the x value of my vertex, which is the midpoint, right, of our zeros. So we can say x value of my vertex is going to be at 300 plus 0 divided by 2. So that's going to happen at 150. Okay, so 150 will represent my x value. Remember what our x value represents in this equation. We'll come back to that. So let's sub that in. So we'll sub that in to find the y value of our vertex. So remember, area equals 450 minus 1.5 times, we just found our x value to be 150. And then that's going to be times 150. So 450 minus 1.5 times 150. 1.5 times 150 is going to be 225 times 150. So 450 minus 250, or 225 is 225 times 150. So our area is going to equal 33,750. And remember, this was also the y value of my vertex. So we can say that vertex is at 150 and 33,750. Well, this represents our width, and this represents our maximum area, right? Because that's our vertex. So if that's the case, then we know our width, we know our maximum area. The only other thing we're going to need is our length. So if that's our width, we can say, okay, well, our length is going to equal 450 minus 1.5 times 150, which we already kind of solved for when we were finding our y value. So our length is going to equal 225. So it's wanting us to find the dimensions that will give us our maximum area. We can say, therefore, you will have a max area of 33,750 meters squared with a length of 225 meters and width of 150 meters. Okay, so when you have these optimization problems, we're always coming back to what are they looking for, our zeros or our maximum? And then depending if you're in factored, standard, or vertex form, how do we actually identify that vertex? Okay, that is all for your note for today.